Hello, and a very warm welcome to today's Nucleic Acid Insights webinar titled Sharpen Up Your RNA and LNP Quant with Stunner. I'm Alison Gash, an editor at BioInsights, and joining me today is Kevin Lanz, who will discuss how Stunner provides rapid and precise LNP characterization with RNP quantification, purity checks, and aggregation detection, helping accelerate optimization while saving time, material, and effort. After the presentation, we'll have a live Q&A session. We invite our audience to pose their questions to our speaker using the Ask a Question box at the bottom of your screen, and we'll try to get to it during the session. Now, I'd like to introduce our presenter. Kevin Lanz, the Global Stunner Portfolio Lead at Unchained Labs, specializes in biophysical characterization of LNPs, proteins, nucleic acids, and viral vectors, with a PhD in bioengineering from the joint UC Berkeley UCSF Bioengineering Graduate Program. So, without further ado, I'll hand over to Kevin to kick us off with the first presentation.
Thanks for the introduction. I'm excited to tell the story of how Stunner can help you sharpen up your RNA and LNP quant and characterization. I used to wear glasses, some pretty severe ones. So I'm going to begin by showing a slide like this and saying that the world used to look like this to me too blurry and uncertain to really know what was in front of my face. When this is the kind of information you're receiving, every time you want to take a next step, there's a lot of uncertainty involved. If I think about it, that ties nicely to the role of analytics in therapeutic development and production, especially for LNPs. Clear, precise, and comprehensive analytics before and after making your LNP can make the difference between choosing the right decision to move on to your next experiments right away or putting everything on hold to wait for, ready? Clear answers. So when we're making an LNP, one of the first steps we have to understand is how much RNA we have in our aqueous phase. In other words, how much RNA are we able to quantify so that we know what our appropriate NP ratios are and we were sure we're using the correct concentrations that we're intending for our therapeutic payload. Then we're going to mix our aqueous and our lipid phases together. Here we're showing mixing them together on a Sunny chip that is used by our Sunny Suite Sunshine and Sunscreen LNP makers. And at the end, those two phases are mixed together and assemble so that the ionizable or cationic lipids are facing RNA at the core of a LNP, where we now have to again quantify how much RNA do I have and add on the question, what size is my LNP that I've made? That's where Stunner helps you answer these questions about your LNP characterization. It gives you answers using UV-Vis and dynamic light scattering on total RNA quantification, sizing and polydispersity, particle concentration of your actual LNPs, and aggregation. So this talk will cover how Stunner delivers answers in those four parameters, how it's unique in its ability to deliver those capabilities, and how it can be used to screen through different LNP formulations and buffer compositions for stability, for aggregation, and especially when you're screening against freeze-thaw stability studies. So when it comes time to measure an LNP sample on Stunner, how it works at the simplest level is by taking your sample and adding it into any of the wells in a 96-well Stunner plate. So each one of those wells is in the same 8x12 format that you're used to in a 96-well plate, except instead of a well, it's a tiny microfluidic circuit where it takes in 2 microliters of sample volume, typically undiluted sample volume for LNPs. And then inside of the Stunner instrument, it will take that sample and pass it through 2 microcuvettes where UV-Vis is read for concentration measurements and the right kind of DLS is done for sizing measurements. So we'll often refer to the DLS done by Stunner as fit for purpose DLS because it's the right kind for larger things as well as the right kind for smaller things. We'll dive into that topic in a little bit further on the talk. Here's what that looks like when I'm loading a Stunner plate. In this case, I'm using fluorescein and a blacklight just to make the sample pop on camera. But as you can see, to load each sample, you simply pipette in 2 microliters into that well, and the sample wicks into the plate through capillary action. Super easy, super simple, and that was shown in real time. Once UV-Vis is read, you get pure and simple quant. So based on the UV-Vis absorbance of your RNA, typically the absorbance at 260 nanometers, you can understand how much RNA is there. Stunner does this incredibly accurately and precisely, and actually what we're seeing here in the graph is octuplicate samples, where each line is overlaid, and you can see how narrow that band is, that these results are incredibly precise. Stunner is able to quantify RNA across a range of 1.2 to 11,000 nanograms per microliter, which definitely hits the range for RNA LNPs. And importantly, Stunner is also able to look at the shape of the RNA absorbance to understand if it's pure RNA that you're quantifying. So once RNA is read in Stunner, then it starts to analyze the shape of that absorbance. If I'm doing this on a sort of more traditional UV-Vis spectrometer that doesn't have advanced analytics, what I might just do is get an A260 value and convert it through an extinction coefficient to a concentration, and maybe I'll look at the quality ratios to understand how pure my sample is, but even if those quality ratios are off, the best answer I can get is a simple A260 absorbance at 260 nanometers. Stunner is a little bit smarter in that it can understand, after that RNA absorbance read, what level of RNA and what level of impurities are present in your sample. So once we have our measured RNA spectrum in blue, it can actually fit for RNA and a small subset of impurities to understand how much of my sample is RNA, what level of impurities I have in that sample, and what my accurate concentration of RNA actually is. So in this case, we're actually looking at impurity from proteins, which could be from an enzymatic reaction like IVT, where I have something left over. We can also look at the concentration of RNA even with DNA contamination. This is because of subtle differences in the absorbance of uracil and thymine. And so RNA can be unmixed from DNA, in most cases by Stunner, to understand the concentration of RNA and how many impurities are present in my sample. And this is something where we've tested out the concentration of RNA and DNA across a range of RNA concentrations, across a range of RNA-DNA ratios, and it holds up pretty well in its ability to see how much DNA is present in your sample. Next, we'll take a look at quantifying RNA inside of a cloudy LNP sample. So here we're looking at that image that's a little bit less blurry than the first time we saw it, and we're understanding that, man, if only we could see through the cloudiness rolling in on the Golden Gate Bridge, we could see some really spectacular things. That's just like that cloudy, turbid nature of LNP samples. If you could see through that turbidity, you'd be able to gather some really spectacular data. Here I'm showing the turbidity or cloudiness of a real LNP sample. So typically when you think about characterizing this and you're thinking about quantification and trying to speed it up, if you want to go fast with quantification, you go to UV-Vis. But nanoparticle solutions are typically so turbid and cloudy that they block most of the light. So traditional UV-Vis approaches fail. And that's not a problem on Stunner thanks to its very narrow path lengths. Here we're seeing an LNP sample in a Stunner microcuvette. To read the sample, Stunner has pumped the LNP into the 0.7 and 0.1 millimeter microcuvettes, where it's able to see through that turbidity and actually understand the absorbance of the LNP sample itself. Even if we can see through an LNP sample, we're met with a second analytical challenge, kind of shown on the left here. So even though we're able to make an absorbance measurement, the absorbance that we measure is actually dominated by that turbidity. Even though the light can get through, it's still measured in that sample. That's shown by that sort of predominant decaying absorbance that I'm kind of highlighting with my mouse pointer. What Stunner is able to do with that turbidity is deconvolute out that decaying absorbance or decaying turbidity signal and understand the underlying absorbance signals that are present. So what's shown on the left versus right is the raw absorbance where we haven't done anything to process that signal on the left, and on the right we're subtracting out the turbidity, which is the lighter gray line, and understanding how much RNA is present in the sample, and then underneath that how many lipids and buffers are present in the sample as well. So this is all done without the need to blank, and for a standard RNA LNP that doesn't have any UV absorbance in their lipids, we're able to get very fast and efficient answers on the total amount of RNA present. When we do this test across a whole plate of LNP samples on Stunner, we can see amazing precision. And here across 96 samples and a single LNP sample, we see a percent CV of 1.54%. If we want to analyze something that's a little bit more complicated, we can say look at a RNA LNP with a protein or antibody conjugate to the outside, maybe for targeting. And Stunner can still unmix those samples because it understands the absorbance coming from the protein sample, shown here in a dark blue, and get you a concentration of how much total RNA is present in a sample and how much total protein is present in your sample as well. Where we can start to use those total RNA answers is by kind of curing some of the hassle of encapsulation efficiency. So if you have your LNP in solution, it's going to have RNA both inside the particle and outside the particle. The percentage of encapsulated compared to the total encapsulated and free RNA will be the encapsulation efficiency. In other words, the efficiency with which RNA is trapped within the particles compared to what is wasted outside of the particles. Typically, people are looking for encapsulation efficiencies of over about 85%, depending on the process. So people are really mostly only interested in efficient processes, which makes sense given the cost of RNA involved here. So when you're trying to understand both arms of this encapsulation efficiency assay, you have to do two separate assays. For the free RNA, you add your dye, commonly ribogreen, which becomes fluorescent when it's bound to RNA. And then for the encapsulated RNA, you need to go through a detergent step to lyse your LNP, make it accessible to your fluorescent dye, and then understand a quantification of your total amount of RNA. Now that assay is pretty complex, where we can fit about 12 samples on a 96-well plate, because that includes the 12 samples themselves, samples at dilutions in ribogreen, samples with dilutions in ribogreen and surfactant, a calibration curve for each of those conditions, and then some necessary blanks. But thanks to Stunner, we're able to understand the total concentration of RNA from UV-Vis, so we can eliminate half of an assay and instead use Stunner to get total RNA without any lysis step. Here's what that encapsulation assay would now look like if we're using Stunner for the total quantification of RNA. We have our same, traditional 12 samples that we're used to getting for free RNA with ribogreen, but now we only need half the amount of ribogreen because we've eliminated half the assay. With that spare real estate on the plate, we can add 12 additional samples. We could double the sample throughput, in other words, and we can half the number of samples since we've gone from using 2 plates for 24 samples to 1 plate for 24 samples. And we can parallelize everything to be more efficient with our time, reading total RNA quantification on Stunner in about half an hour and reading the free RNA quantification on the fluorescent plate reader in about 20 minutes. That allows us to speed up our quantification. Here we're showing some numbers for 24 samples to get answers on total RNA, encapsulation efficiency, and size and PDI from light scattering, which we'll cover next. As we see in the classic method to analyze 24 samples, we'll get things done in about 3 total hours, where 2 of those are at least going to be hands-on. And in the hybrid assay, we'll have hands-on for a little bit less than 30 minutes, with a total time of about 45 minutes if we take advantage of all the parallelization that we showed. Now that we've shown all the benefits of the improved hybrid assay using Stunner for total RNA, we do want to benchmark it between Stunner and ribogreen for concentration of total RNA. That we could see here across a panel of 3 different lipid compositions making LNPs in 2 different buffers. We see good agreement between the 2 assays. And if we then combine that data to calculate encapsulation efficiency between the ribogreen for free RNA and the Stunner for total RNA, we see even better agreement in encapsulation efficiency quantification. So all in all, applying Stunner's UV-Vis for RNA quantification in your LNP for the total RNA part of the encapsulation efficiency assay, it saves you half the time, half the dye, half the standards, and doubles your throughput. Now that we've been through the quantification part of Stunner's approach to LNPs, let's pivot to sizing. So when it comes to sizing, here's the basic problem that needs solving in the world of DLS. Antibodies and LNPs are vastly different sizes. They don't behave the same way when they interact with laser light. You need different applications for different molecules, since a one-size-fits-all approach doesn't fit for every different sized molecule. In other words, you should be using fit-for-purpose DLS. When Stunner runs its fit-for-purpose DLS, it's going to give you all the size data you need, intensity distributions, mass distributions, and number distributions, so that you fully understand the size of the particles that you're working with. But let me dive into exactly why DLS angle matters for LNPs and why we talk about fit-for-purpose DLS. So for those small things like antibodies, they will scatter light evenly in all directions. So kind of regardless of scattering angle, you get the same z-average size because light is being scattered isotropically or equally to all different angles. When you look at LNP samples, if you have a nice homogeneous LNP sample, this is actually true as well. So across different scattering angles, you'll have the same z-average diameter. However, once you start to see small populations of aggregates in your sample, and indeed the problem persists for larger populations of aggregates, then in your LNP sample, size will depend on the angle where you measure it. So in this case, as you change scattering angle, z-average size changes. This is because those aggregates present in your sample have an angle-dependent or anisotropic light scattering. So wherever you measure the resulting light scatter from will influence the z-average size that you arrive at. That's why it's important to understand the full picture of your LNP sample and indeed measure at multiple angles for your dynamic light scattering. Stunner solves this problem by taking a single DLS detector and rotating it through multiple angles. This gathers data, typically at 7 angles, to get enough info to handle larger particles properly. We call it rotating angle dynamic light scattering, or rattles, and this is what it looks like as the detector rotates around to different angles. To prove the benefits of looking at different angles by rattles, we're going to run a spike-in study. We'll take a good LNP sample of about 80 nanometers in diameter, that's going to be nice and homogeneous, and we'll add in an aggregated LNP sample that's much larger and much more heterogeneous. We'll add small set volumes of that large aggregated sample into the good sample and see what we can measure by rattles. First, we want to characterize each of these samples, of course. So here we have the good sample with an z-average diameter at 0 degrees of about 78.9 nanometers and a PDI of less than 0.1 and very nice sharp distributions by intensity in green and mass in blue. Our aggregated sample has a much larger z-average, a much larger PDI, and you can see how there's lots of aggregates present in the distributions. To analyze these mixed samples, we're going to use 2 data points. First is z-average at 0 degrees, which is the extrapolation of all the DLS info that Stunner has to the 0 degree scattering angle, and gives you one clear output that is angle independent, meaning you have the best ability to look at the average size of all your particles in solution and not miss aggregates because of the angle your DLS uses. We'll compare that z-average at 0 degrees to the z-average that you would get from a backscatter angle. Those are the angles nearest to 180 degrees, where the laser basically bounces back out towards itself. Those angles are most likely to miss aggregation. If we look at our spike-in study, we can look at those backscatter angles first. As we add more and more of our aggregated LNP to our good sample, the average size by backscatter DLS doesn't actually see any change in size. In other words, backscatter DLS is really not helpful in understanding or detecting that aggregates are present in our sample. But if we look at the z-average at 0 degrees, where we're taking into account all of the information from all of the angles that Stunner gathers with rattles, we see a significant visible increase in our z-average size, going from 78 nanometers all the way up to 244 nanometers, which is a very clear response that we now have aggregates present in our sample. Next to this sizing information, we also deliver particle concentration information. So if we're measuring a small LNP or a large LNP, we can also understand the light scattering behavior of that by looking at all of the angles, understanding the scattering intensity, and calculating how many particles per mil should be in each of those samples. Okay, so the last example I want to show is one where we've taken LNPs produced on sunshine, and in this case, we're going to look at a variety of lipid formulations and a variety of buffers, which is easy to create on sunshine, and it's easy to create an appropriate volume for a bunch of analytics that you want to do downstream from your LNP samples, and then do so with reusable microfluidics, where you can reuse and wash and reuse the glass sunny that is being run by the sunshine, and continue to create more and more LNPs at a very efficient cost for each of those microfluidics. There's three different formulations that we're going to be looking at here. The standard one is based off of Moderna's spikebacks in green. Always shown in blue is our DOPE formulation, where we've swapped out the structural lipid DSPC for DOPE. And the one shown in gray is the ALK 0159 formulation, where we've changed DMG PEG 2000 to ALK 0159. We'll be evaluating these three different lipid formulations against 8 different buffer conditions. They look at different buffers like PBS and tris, and the different concentrations of sucrose and mannitol. So analyzing these experiments quite simply, we can look at what backscatter DLS sees. So in this case, across all of our different buffer conditions and all of our different lipid conditions, we see a fairly consistent z-average backscatter size. But once we start to look at z-average at 0 degrees, we start to see some samples stick out as performing more poorly with regard to size, and that indicates that aggregates are more of a problem in those samples, and indeed that's more present in the DOPE samples on average. If we then want to test those conditions against freeze-thaw challenges, down to -20°C and back up, we can again analyze them for backscatter sizing, where we can't see much of a difference in the majority of cases. And the way I'm analyzing these as a very quick screening method is to look at what's above or below 100 nanometers for my z-average backscatter size. And indeed, about 60%, 58% of the samples pass that threshold. So this backscatter DLS approach really is unable to screen out the bad samples with kind of backscatter sizing. But if we use a sizing technique that is sensitive for aggregation, the z-average technique that incorporates all of the angles and produces the size at 0 degrees, we can see that 4 out of our 24 samples, 17%, actually have sizes below 100 nanometers, and those indeed are our very best samples when measured by size, and they truly stand out when you use the appropriate fit-for-purpose sizing technique. Importantly, all of that DLS information is incredibly fast to gather. We have about 10 minutes of hands-on time on Stunner, where gathering that much DLS information on a cuvette-based method would take hours and hours and hours. And that's how Stunner delivers label-free, standard-free, and hassle-free nanoparticle characterization to the nanoparticle world. And hopefully with Stunner, you can cut through the fog to see all the spectacular details of your LNPs. Thanks for attending this talk, and I'd love to stop and take questions, and if you think of something later, love to extend the conversation about science, and so please reach out to info@unchainedlabs.com. Now let's take some questions.
Great. Well, thank you, Kevin, for that great presentation. So now we're going to answer some questions and start the Q&A. So as you're on camera, we will start with first question from our audience. How long does it take to run a full plate of samples on Stunner?
So if you're doing just UV-Vis, so this would be like if you're quantifying your RNA only before creating an LNP run, that'll take about 10 or 15 minutes. If you are starting to run sizing and you want to look at LNPs, you're going to run a rattles sizing run, and that'll take about 2 hours, maybe slightly longer than 2 hours. So it kind of depends on how much data you're hoping to get out of those samples. UV-Vis runs really quick. DLS takes a little bit longer, so anywhere between 10 minutes and 2 hours.
Great, thank you. And our next question, do you need to dilute your LNPs to get answers?
Typically, no. Most customers can just use their LNP samples neat, however they finish their formulation of them. If there's rare situations where an LNP sample is hundreds of nanogram per microliter RNA, you might have to do a 1-to-1 dilution, but most customers don't need to dilute samples. The only exception to that is if you have high concentrations of ethanol still present in your sample because they haven't been cleaned up yet. Stunner wants that ethanol percentage to be below about 20%.
Great, thank you so much. And on to our next question. Using the unmix algorithm, are we able to isolate the absorbance spectrum of the impurities to tell what they are?
Oh, this is an interesting one. So unmix is kind of like if you're trying to solve a puzzle and you have one last piece missing, it's a really good way of figuring out what needs to go there. So if you have an impurity that you're looking for, like say you are quantifying RNA and you're expecting protein, there are definitely ways you can set up Stunner's unmix to help you quantify that amount of protein that's present. But it's not going to be able to look at the spectra and figure out the ID. But if you know what the ID is, then you could definitely set up Stunner to be smart and kind of deconvolute all those UV-Vis data points it's getting to understand what's actually present and at what concentrations.
Great, thank you. And our next question, can you automate Stunner for sample loading?
Yes, so Stunner is normal, 96 well plate SPS compatible, which just means it's in that normal 8x12 format, and the wells are where you'd expect them to be for loading with the robot or loading with an 8-channel pipette head. Those things are pretty easy.
And our next question, is there an advantage to running raddles on smaller molecules like proteins?
So this is actually why we talk about DLS as kind of our fit for purpose DLS. So when you're running small molecules like proteins, they're going to be those isotropic scatterers. And so you would actually want to run single angle DLS, frankly, just because it's faster, and running the extra angles on DLS is not really going to add much value in terms of new information that you can get. So if you run that single angle DLS on proteins, then you can get that DLS down to about 1 hour for a full plate read. So basically,
Amazing.
we recommend a single angle DLS read for proteins.
Great, thank you. And our next question, can you take Stunner downstream?
Yes, so Stunner has 21 CFR Part 11 software tools that are easy to kind of turn on for the software. Make sure that all your data is protected behind those audit trails and signatures. There's also a variety of IQ/OQ services. There's PV services to perform UV or to confirm UV performance against the USP and European Pharmacopoeia. So Stunner's got a lot of tools that make it easy to transfer downstream.
Thank you. And our next question, how does the Stunner handle the more dilute samples if the sample well is fixed at a very small path length?
So Stunner's got a very sensitive UV-Vis system, so it's able to get down to concentrations that are very low. So typically, if you're making LNPs, you're going to see concentrations that'll ideally be around 50 nanograms per microliter. Now, you might be an order of magnitude higher, you might be half of that, but those are going to fit very squarely within Stunner's absorbance range. And then you can also get way lower on that when you're looking at RNA, or if you're looking at RNA LNPs, and you want to get into the tens or single digit microgram per mil, that's no problem.
Great, well, amazing. Thank you for answering those questions, Kevin. Sadly, that's all we've got time for today, but any questions we didn't get to, we'll reply to them by email. This webinar will be available on demand tomorrow, so look out for an email from us with the link. And we'd also like to invite you to take a short survey to provide us with feedback on today's webinar, the link to which can be found in the resources on the right-hand side of your screen, as well as in the on-demand email. Additionally, you'll find an attendance certificate available on the right-hand side of the screen. And all that's left is to thank Kevin once more for a great presentation, and thank you to the audience for listening. We'll hope you join us again soon.